Right. Hi, everybody. Welcome back to section 6.2. And in this video, we're going to solve another second order linear differential equation with functions of x as our coefficients to the y. So we want to solve this. So remember, we want to get two solutions that look like, y equals a naught times y1 plus a1 times y2, right? Or y1 and y2 are some type of power series solutions. So it's going to be a long process, but we'll get through it. But remember, that's our goal when we're taking these appropriate steps. So here's a differential equation: x squared plus 1y double prime plus xy prime minus y equals 0. This one's going to be a little more involved than the previous one because we have a x squared, we have an expression times y double prime, and we have another y prime term, so maybe a couple more things to deal with, but same process as always. Just got to follow the path. So let's go ahead and get going. So solution on this. All right. So we want to make sure that x equals 0 is an ordinary point because that'll give us an easier power series solution to work with. So, we'll put in standard form. So put in standard form. Okay, that means I'm going to divide by that x squared plus 1 because standard form means get y double prime naked. Okay, so what I would end up with is, you know, y double prime plus x over x squared plus 1, y prime minus 1 over x squared plus 1, y equals 0. Okay, so, we want to identify the p of x, the q of x, so here, p of x would be x over x squared plus 1, and q of x would be 1 or negative 1 over x squared plus 1. And so with these, right, there's a x squared plus 1 on the bottom, but there's really no domain issues here. Yeah, so like the only thing that would make this go to 0 is if we have like a negative 1 occurring in the denominator, but that x is going to be squared. So like we could never get a negative in the denominator. So there's no chance of that happening. So what that means is every finite x value is an ordinary point. Okay, so since every x value is an ordinary point, then we can for sure choose that x equals 0 is an ordinary point. And we could center our series around that point. So x equals 0 is an ordinary point. So a power series centered at x naught equals 0 will converge. Okay, so great. That means we can set up our power series solution to be y equals a series n equals 0 to infinity a sub n x to the n. Because x equals 0 is an ordinary point, so, we could do this if we want x minus 0 to the n, but yeah, that just means x to the n. Okay, and we can take the derivatives now because we're going to need a y prime. We're going to need a y double prime. So let's take those derivatives, but those are standard derivatives. We know what those would look like by now. So series was starting out at 1, n times a sub n, x to the n minus 1, and the second derivative would be y double prime, index starting now at 2, n times n minus 1, a sub n, x to the n minus 2. Okay, so now what we want to do is plug these derivatives and y into the differential equation. So then plugging into the differential equation. So what's the differential equation? It's x squared plus 1 times y double prime plus xy prime minus y equals 0. So yeah, we're just going to plug in our power series now. So this would be x squared plus 1 times the power series n equals 2 to infinity, n times n minus 1, a sub n, x to the n minus 2, plus x times the series n equals 1 to infinity, n a sub n, x to the n minus 1, minus n equals 0 to infinity, a n, x to the n. And it all equals 0. Okay, great. So this is our setup. And now what we want to do is start distributing. So, we could distribute in this expression x squared plus 1, distribute in the x. And so what we're left with, we could even distribute in the negative. But what we have now is x squared. Let me move over here a little bit. We would have x squared times a series starting out at n equals 2 plus 1 times that series starting out at n equals 2 plus distributing the x now. It would be n a sub n x to the just x to the n. And if we distribute in the negative, it would be plus starting at a 0, negative a sub n x to the n, all equals 0. Okay, so yeah, just be careful with your algebra here, because we are splitting this up. Both of those terms are multiplying the same power series. So then let's go ahead and distribute those terms in now. X squared and the 1. We don't have to do anything with the 1, so we're just worried about the x squared. So this would be starting out at n equals 2 now. N times n minus 1, a sub n, and then this will just be x to the power of n. And then I'm just going to rewrite these terms here because nothing is changing for these. Okay, so this is our setup. We have 4 terms right now. Okay, so what we want to do with these 4 terms is we want to have the same, we want to combine these, right? So we want to have the same index and we want them all to be x to the n. So let's take care of both of those. Okay, so now we want to have all of them to be x to the n. All of them are x to the n except for the second term. So let's index shift the second term to be x to the n. So that means we're going to, you know, add 2 to everything in the series, subtract 2 to the index. Okay, so what this would look like is just going to rewrite these other 3 series. They're not changing at all. And I'm index shifting my second series. So this will start out at n equals 0 now. And I'm adding 2 to every single term in that series. So this would be n plus 2 times n plus 1, a sub n plus 2, x to the n. And then everything else just stays the same with these other two series. Okay, so all my terms are now x to the n, so that's good. And now what I want to do is have them all be the same index. So I have a couple n equals zeros, I have an n equals 1, and I have an n equals 2. So what I want to do, since n equals 2 is the highest index, I want them all to be n equals 2. So, now we want all the indexes to be n equals 2. So we want, x to the n equals 2 for all. Or let's just say for all. And so what do we need to do? We need to peel off terms. All right, so I need to peel off n equals 0 and n equals 1 for this second term. I need to peel off n equals 1 for this third term, n equals 1 and n equals 0 for this fourth term. So just be careful with your algebra when you're plugging in these terms. I'm gonna put brackets just to show like the the different peeling off. So for this first term, it's already at n equals 2, so you don't have to peel anything off there. But the second term, we need to peel off n equals 0 and n equals 1. So what that would look like is 2, we put brackets, 2 times 1, a sub 2, x raised to the 0. That's for n equals 0, plus, I'm plugging in n equals 1 now. This would be 3 times 2, a sub 3, x to the first power, plus the series is now starting out at n equals 2. Okay, so that is the second term. Let me say this is for n equals 1. So let's take care of the third and fourth term. So I'm going to continue it on down here just so I'm not scrolling back and forth a lot. So this is going to be that third series. So it's starting out at n equals 1. So I need to peel off n equals 1. So this would be 1 times a sub 1 x to the first power, and then plus the series now starting out at n equals 2. Okay, so not so bad for that one. And this fourth term, we need to peel off n equals 0 and n equals 1. So we peel off n equals 0. This would be negative a 0 x to the 0 minus a 1 x to the 1 plus the series. So that one not bad as well. I think the only bad one was the second term. So n x to the n. Okay, and this all still just equals 0. N equals 0 and n equals 1. Okay, so a lot of moving terms going on. We could rewrite a couple things, clean it up, but let's just keep it a little short. for this. There's a lot of moving parts, or a lot of tedious parts. So what we want to do is group to get to our recurrence relation. What we want to do is group the x raised to the zeros and x raised to the ones, and then the series, that we essentially have now starting out at n equals 2 and x to the n. So let's group those together. You could double check it if you want. But yeah, we're just going to group together all of these terms with x0, x1. So let's go ahead and do that. So this would be 2a2 x to the 0 minus a naught x to the 0 plus 6a3 x to the first plus a1 x to the first minus a1 x to the first. Okay, plus, now I'm just going to combine all of our series. Put some brackets there. This would be a sub n times n minus 1 plus a sub n minus 2 times n plus 2, n plus 1 plus a sub n times n minus a sub n. All this times x to the n because we factored that out, and it all equals 0. Okay, so did a lot of algebra to get to this step we just did, but double check it, maybe pause the video, see how we got there, but just for the sake of time, we don't want to like write out every single little step for right now. Okay, so before we get going on our recurrence relation, what I want to do is clean up the inside of the power series a little bit. So what I want to do is clean up really these terms here. It's a bunch of AN. So like let's clean up the ANs. All right, this will make it a little easier for us when we get going on a recurrence relation. So, let's clean up the ANs. So what I'm going to do is, let's say I'm going to factor, or let's rewrite it like this. I'm going to write it like a sub n times n minus 1 plus a sub n minus n. So we're going to clean this up. I'm going to factor out an a sub n. So this would be like n times n minus 1 plus n minus 1. Okay, and then we can clean this up a bit more, distributing that n. So this would be like n squared minus n plus n minus 1. Well, that factors into, or excuse me, not factors, but the n's cancel out. So n squared minus 1. And so I could write it like n plus 1 and minus 1. Okay, so I wanted to clean up those two because that was bugging me a bit, and I want our recurrence relation to be pretty clean. So let's keep moving along. We're almost there. Now it's almost time to set up our recurrence relation, right? So this is my new term I could use inside that power series. It cleans it up a bit. So we have for recurrence relation. So here I'll say, let me come over here a bit. Set up recurrence relation. Okay, so we have 2a2 minus a naught equals 0. Getting that from right here. Okay. And the a1 and negative a1 cancel out, so that's good. That equals 0. So 6a3 equals 0. And this is for n equals 0. This is for n equals 1. And then this whole term right here in the power series is going to be what's going to help me establish my pattern. So what it's going to be is a sub n times n plus 1 times n minus 1 plus a sub n plus 2 times n plus 2 times n plus 1 equals 0. And this is for n equals 2, 3, 4, etc. Okay, so we want to set up our recurrence relation. So what we do is solve for the highest a sub n. And in that case, it's going to be a sub n plus 2. So I'm going to move everything over to the right side and isolate a sub n plus 2 when I solve for this. So if we finalize our recurrence relation, we could see from our first term that a sub 2 equals a naught over 2 for n equals 0. Okay. Next one is a sub 3. A sub 3 equals 0. Easy. For n equals 1. And here's where we get our big recurrence relation that a sub n plus 2 is going to equal negative a sub n times n plus 1 and minus 1 all over n plus 2 and plus 1. Okay, and that even helps out a little bit. Things actually cancel out here. The n plus 1s cancel out, so that works out well for us, something less to worry about. So we get a sub n plus 2 equals negative a sub n times n minus 1 all over n plus 2 for n equals 2, 3, and 4. Okay, so now we have a recurrence relation. And so we're going to use this recurrence relation to get two solutions in terms of a naught and a 1. Okay, let's do it. So we have for n equals 0, n equals 0, we have just a2 equals a naught over 2. I just have that from up above right here and then setting it up right here. All right. So that's what I have already. Move on to n equals 1 now. I also have that. I have that a3 equals 0. And now let's get into our relation for n equals 2. I'm going to plug in n equals 2 into here. All right, so what I end up with is a4 equals negative a2 times 2 minus 1 over 2 plus 2. That equals negative a2 over 4. But I know what a2 is, right? I know what that is. I know it's a naught over 2, so I could rewrite this as negative a naught over 2 all over 4. And so I end up with negative a naught over 8. So a4 equals negative a naught over 8. And I guess I'll box these two. Okay, so let's do a couple more, right? We have two A naught terms. I would want um, a couple more to see if an A1 is going to come up. So let's try n equals 3. So if I plug in n equals 3 into my recurrence relationship, what I would get is A5 equals negative A3 times 3 minus 1 all over 3 plus 2. And I know A3 equals 0. So that means this whole term is just going to be 0. So that means A5 equals 0. Okay, so we have a couple zeros here. Let's try one more. Let's see what happens. Am I getting an A1 or am I getting another A naught? So if I plug in n equals 4, I get negative A4 times 4 minus 1 all over 4 plus 2. Um, A4, or I know A4 is negative A naught over 8. So what I end up with is negative 3 A4 all over 6. So it's negative A naught over 8 all over 2. So that would be A naught over 16. And so that's A6 equals A naught over 16. All right, so I'm only getting A sub zeros, A naughts. I'm not getting any A1s. So the power series solution, it looks like Y equals A naught plus A1x plus A2x squared plus dot dot dot, right? What this looks like is A naught plus A1x. Those don't change at all, right? Because the only ones we found were A2 and above. But then we start plugging in our A2, A3, A4, A5, A6. So this is going to be plus A naught over 2x squared plus 0x cubed minus A naught over 8x to the fourth plus 0x to the fifth plus A naught over 16x to the sixth dot dot dot. So if we clean up all the zeros, okay, we found a couple. What we're left with is A naught plus A1x plus A naught over 2x squared minus A naught over 8x to the fourth plus A naught over 16x to the sixth dot dot dot. Well, all of these are A naughts and I only have one A1. So if I group together the A naughts and I just have the A1, what this would look like is A naught times 1 plus 1/2 x squared minus 1/8 x to the fourth plus 1 over 16x to the sixth plus dot 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 plus A1x. And that's essentially my answer. Because what is this? That's y1 and x could be y2. It doesn't need to be infinitely continuous, like as long as it's some type of solution. Because remember, a solution is y equals A naught y1 plus A1 y2. All right, that's the solution we're trying to get. But okay, thank you for watching. Yeah, quite a long problem. Hopefully, you're being careful with your algebra when you're doing these problems. That's always the main goal, just keeping track of your algebra and making sure everything's lining up. They take a long time, so take your time with these. But thank you for watching, and I'll see you in the next video. Take care.